You have to do that once with a subset of reads, so it's super simple to do it.
And then you just basically the central limit theorem tells you that you could do the test for the mean, you don't have to assume normality.
Exactly, and that's one thing. Further improvements of this, although we're not looking into that, further improvements is for insertions where you have fewer observations, you will have less power to detect them, so you would want to do some exact testing. Yeah, but yeah, it's based on central limit theorem. Yeah.
Do you hear me? Okay, perfect. Oh, no. Yeah, it was working. Checked it.
Try to go and navigate through the space. It's not on. But you go to display.
Oh, now it's working. Hey, thanks everyone for staying. I'm Farhad. I'm from Lazarevsky Group, and if you don't know him, he's the one who is organizing the program. And today I'm going to talk about fine mapping and post-GWAS era. It's a little bit vague title. I try to make it clear in the next slide. So we heard a lot about genome-wide association studies and how people do that. It's a process that you collect individuals who have disease called cases and individuals who are healthy called control. You collect their genetic information and then you perform some statistical tests. And the output of this statistical test will be the significance score for each variant that you can plot it in this diagram that I'm showing, which usually refer as the Manhattan plot. And the x-axis is the variant position, and the y-axis is the significance score for each variant. And the higher the significance score is, the higher the correlation or the association of that variance to the trait or the disease. Now, GWAS was very successful to find thousands of variants that are associated with different disease. But the question that in our lab we are interested in is that how many causal variants exist in a specific loci? Now, I have to mention that the word causal here shouldn't mix with the word causality that people use in statistics or introduced by Judah Perr. Here, a causal variance is a variance that is responsible for the peak of association. Now, the next question that we are interested in is that can we actually find this causal variance? And today, most of my emphasis of my talk will be on how to find this causal variance, and this is referred as fine mapping in the literature of GWAS. And the last question is actually, can a SNP be causal both in two different studies, both in, for example, in an EQTO and a GWAS? And this is usually referred as colocalization. Now, why I'm mentioning these three works, actually they are very similar to each other. If you can compute what's the probability of a variance is causal, then you can see actually you can solve all these problems. Now, I will emphasize on the fine mapping part, and you may ask that why this problem is hard. It seems like a very easy problem. Just pick a significant threshold and consider anything above that to be causal. So here we are trying to zoom into one of the region, and you pick this red horizontal line as your threshold to consider any variance above it to be causal. But you can see there are too many variants that pass your significant threshold, so it's not very easy to say which of these variants are actually causal. And the reason this is happening, most probably one of these variants are causal, and all the variants are in LD with this variance, and they seem to be significant as well. So how can we solve this problem? So if I give you a very simple region, let's say I give this region which have 35 SNPs shown on the x-axis, and the y-axis is the significant score for each variance. And the gray triangle, I hope you can see it, is actually the LD structure, which every square or diamond inside this LD structure is a pairwise correlation between two SNPs. And the darker the diamond is the higher the correlation, and the lighter the diamond is the lower the correlation. Now, if I ask you which SNP can be the causal, it's actually very easy to answer this question. You pick the pig SNP, and you say this SNP is actually causal. And actually, your intuition is right. This is the SNP that we implanted to be causal, and you can easily detect. So you may think that this problem is easy, so why I'm not talking about it. In some examples, it's actually not that easy. So here I'm showing you a more complicated example that is not intuitive just using your intuition, that by looking at the LD and the marginal statistics, you say which variance is causal. And now you can actually pick which variance that you think is actually causal, and later on I will show you the right answer and see if you can detect the right one. So formally, fine mapping is that given the marginal statistics that you computed from a GWAS result, can you figure out which variance is actually causal? And this problem is hard for two reasons. One is the linkage disequilibrium, means that variants are not independent. And this makes the problem hard for two reasons. One is the computational reason, is that if two SNPs are not independent, you can't break them and solve the problem independently. So it's computationally makes the problem hard. Another fact, if a variance is causal in LD with another variance, you see the effect of the causal variance in another variance. So when you observe a statistical score for a variance, you are not sure this statistics is coming from the variance itself or is just tagging the effect of another variance. And another reason that this problem becomes hard is that there can exist more than one causal variance in a region that you're studying. Now, there are a couple of methods that was proposed to solve this problem, but I will only talk about two of them, and then I will talk about our method. So the first method, which actually is very simple and intuitive, is just pick the top k most significant SNP based on their p-value. So here I'm setting k to equal to 5, and I'm running on the complicated region, and the black arrows are representing the most significant SNPs that is picked by this method. So you may assume that, oh, this method may work very well. Now, I will show you the true answer of this complicated region. So the red triangle are actually the two causal variants that we implanted in this region. So you can see when the k was equal to 5, we couldn't find the actual causal variance or any of the causal variants that we implanted in this region. In this example, we implanted 2. And another problem with the top k method is actually ignores the LD. No matter what was the LD, the top k algorithm will always give the same answer. So it's kind of ignoring the LD. And the other problem is that finding the right value of k is actually very hard. If you want to know what is the right value of k, you should know which variance is actually causal. And in that case, you already know the answer. So the second method, actually very elegant, is usually referred as the conditional method. So it's an iterative method. In each step, you pick the most significant SNP as causal, and then you recompute the marginal statistics of all the other SNPs, given that that SNP is causal. And you keep doing this till the significant score of all the variants fall below a significant threshold. So let's run it on this complicated example. So the red arrow represents the most significant SNP in the first stage. So you pick that SNP, and you want to recompute the marginal statistics of all the other SNPs. This is equivalent of removing the effect of this SNP from that SNP itself and all the other SNPs in LD with that SNP. So that SNP will drop to 0, and you remove the effect from the other SNPs, and then you pick the next significant SNPs, and you keep doing this process. So if you run conditional actually twice, you can see you can't capture any of the causal variants that we implanted in this region. So this complicated region is actually a problem for both the top k and the conditional method. And you may assume that why this is happening, and you can guess that the reason this is happening both make an assumption that the most significant SNP is always the causal SNP. So we want to see how true this is. So we did simulation, and we took two different regions, one when the LD is actually very complicated, and another case when the LD is actually very simple. And we implanted one SNP to be causal. And we want to see what's the rank of the causal SNPs for these two different scenarios. And you can see when the LD becomes simple, a significant amount of time, the causal variance is actually rank 1. It means that the methods running on LDs, which actually is simple, assuming that the most significant SNP is causal, will work fine. However, when the LD gets complicated, this is not necessarily true. You can see a significant amount of time, actually the causal variance is not rank 1. So you can see it has rank 2, 3, and actually can be high. So depending on how the LD is complex or simple, this assumption is violated, and the top K and the conditional method will perform poorly in these examples. So this motivated us to actually come up with our method. We refer this to Caviar, causal variant identification in associated region, which is actually based on a simple concept called row causal set. So we want to compute a set that can capture all the causal variance with probability at this row. Now in practice, you want to set this row to a very high value, let's say 90 or 95%. So you want to capture all the causal variance in that region with probability at least 90 or 95%. Now I have to emphasize that this doesn't mean that all the variance in this set are causal. What this means, if you go and biologically validate all this variance with probability 90 or 95%, you can capture all the causal variance. So a trivial solution to this problem is just to pick all the variance as your row causal set. If you pick all the variance as a row causal set, and assuming that the causal variance exists in that region that you're looking, so with probability 100%, you can capture all the causal variance. But obviously, this is not a good answer. Among all the row causal set, you want to find the smallest set. And the reason is that this will minimize your validation cost as well. And it's kind of intuitive. You assume that there are very few causal variance in a region compared that there are too many causal variance. So let me show you the output of actually Caviar on this complicated region. So you can see when we run Caviar for a 95% causal set, it picks 7 variants shown by the black arrows. And you can see actually it can capture the 2 causal variants that was implanted in this region. So if you go and validate all these 7 variants, with probability at least 95%, you should be able to capture the 2 causal variants that we implanted. So how does Caviar actually work? It seems like it's not that easy. So in order to find this row causal set, we introduce a concept called causal statuses. So you can consider that for a single SNP, you have 2 possible causal statuses. Either that SNP is causal, which means that it has an effect on the phenotype, so you can represent by 1, or the SNP is not causal, so it's 0 and has no effect towards the phenotype. So for a region which have M SNP, there are 2 to the M possible causal statuses for that loci. Now, for now, let's assume we can compute what's the likelihood of every causal statuses for a region. Then what we define is a concept of a causal set. So a causal set is a subset of the SNPs that you have. For now, let's say this causal set size is K. So there are 2 to the K possible causal statuses for that causal set. Now, we can actually compute some probability. It means that given a region with M SNP and a set of size K, what's the posterior probability that this set can capture all the causal variants? Now, to simplify the presentation, we kind of approximate here, but in actually paper we computed the proper way, is that in order to compute this posterior probability, you sum over the likelihood of all the causal statuses for that causal set. Because the set is size K, there are 2 to the K of these causal statuses. Now, if you divide that by the sum of all the possible causal statuses in that region, which there are 2 to the M, you can compute this posterior probability. Obviously, you have to multiply it by the probability of the causal statuses as a prior to make sure this is a posterior probability, but I'm just omitting that for now. Now, if this quantity is greater than the threshold row, let's say 95%, then you found a row causal set. Now, how do we compute this likelihood? Obviously, doing this 2 to the M is computationally challenging, and that's what I will mention at the end of my talk. Now, how do we compute this likelihood? Let's consider a very simple example. I don't want to go to the detail of the math that much, but what we know is that for a single SNP, the marginal statistics follows a normal distribution with a specific mean and a variance of 1. And the mean is actually referred as a non-standard parameter. So if we assume that you know what is the non-standard parameter in a setting, and I want to assume during this talk that actually someone has given you that, but in the paper we actually generalize and we integrate over all the possible values. But if you know what is the value of this non-standard parameter, so you know what is the mean, you observe the marginal statistics, so it's very easy to compute what's the likelihood of this SNP being causal. Now, if the SNP is not causal, what happens is that the mean becomes 0. So again, it's very easy to compute what's the likelihood of this SNP being non-causal. Now, you can extend it to a more general case when you have two SNPs, and people have shown when you have enough number of individuals, actually the statistics, the joint marginal statistic of these two SNPs actually follows a bivariate normal distribution, which the covariance is actually the LD between the two SNPs. And the mean of the causal variance is the NCP, for example, we know for now. And the SNP that is actually in LD, let's say the SNP A is causal, so we has an NCP of, let's say, lambda C, and the NCP of the non-causal variance, which actually is the SNP B, will be lambda CR. Yes. Well, OK. So you can see that you can generalize this to a more complicated, like all the variance that you have in this region, and the statistics follows the MBM distribution. So easily for each possible causal status, you just have to plug into this distribution function and compute what's the likelihood. However, it's computationally challenging to compute all these 2 to the m. So we make some assumptions. And we make assumption that in a region, there is at most 6 causal variants. Now, you may ask that, well, if there are m SNP, there are like m to the 6. So this is still computationally very costly. And actually, me and Serum are working to make this faster. And there are some ways to do like MCMC or sampling to make it faster. But if you have some ideas, I'm more than happy to discuss with you guys. So in the end, I want to acknowledge people who were involved in this work and the other 2 projects that I didn't mention. We have a software that you can access. And actually, it will solve the other 2 problems as well. And I want to acknowledge Eliza Erskine and Bogdan, who are not here both. And I want to make an acknowledgement and recommendation of going to Phil's and have a coffee. Thank you.
So I have a very naive question.
Yes.
So assuming that your sample size is big enough, so why would a non-causal variance have a higher association signal than a causal variance? Is it genotyping errors?
Oh, well, if it's like between 2, if there are 2 causal variants, they may make one of the SNPs in between to have a higher association by chance.
And also, have you tested how well, how does the size of m, affect the performance? Because sometimes
The performance, you mean the accuracy or the speed?
the accuracy.
The accuracy won't matter that much, but the speed will definitely matter because it's really, really slow.
But I'm saying that in the case of a EQT analysis, sometimes you have to make a choice in terms of how big of region you search, right? So if you say, okay, I'm also going to consider long-range intensive promoter interactions, then you have to search a much larger window. So,
Well, that becomes like, if you can run the whole thing, it's OK, but you can't. And you have to make sacrifice. Like you say, OK, I will ignore some of the variants that actually have very high p-values. So most probably they are not significant. And for cis-EQTL, we run it for GTEx data, and they have like this 1 megabase definition. So for that, it's fine. But yeah, accuracy is not the problem. But if you filter out some of the SNPs, then you may sacrifice the accuracy. But if we make it faster, then you don't have that problem at this
and
point.
also, I wonder, like, if you, once you apply this, you probably have done this, like applying this to some, EQTL data sets. So how well does the identification of causal variance overlap with the annotations of, like, say, transcription factor binding?
Actually, I haven't done it, but Dan Gashfield lab has done. And actually, they found that it's actually a very high enrichment. Yeah.
Okay.
But the problem is that in some cases, when the LD becomes complicated, the set gets big. So then for those cases, you may not rely, because it will pick a lot of SNPs in that region. So the LDs actually can be problematic.
How do you decide on the priors? That's actually, I have to.
The prior causal statuses? OK. Actually, we put a very simple prior that we assume the SNPs are independent. And the probability of a SNP being causal is like 0.01.
Okay.
And actually, it doesn't change that much when you change this number. So.
How sensitive is it to that?
Well, if you make the prior very small or like very, very big, the result will be like, it will pick a very large version. Then. It will pick most of the SNPs. But if you are putting along like less than, if you don't put it too high or too very small, it should give a very reasonable answer in that range.
And then you assume that you have an additive model, right?
Yes, yes.
And so what happens is, it makes sense if you look at a specific
Like
region.
epistasis effect?
Yeah.
I have no idea. We have. Hopefully. But we assume that summary statistics is coming from someone given. So usually people run it in just like an additive model. Right? Yeah.
What happens if the causal variant isn't in the data? What would you output in your causal?
So actually, that will be a problem. So assuming if you're solving the fine mapping problem, that will be a problem. And according to my simulation, it will pick all the variants in that region that are kind of in high LD with that causal variance.
Just tag it.
Yes. And if you don't have power and you run this method on a region that you don't have enough power, it will pick everything again.
Sure. Yeah. And you're saying you have like a package.
Yes.
So
yes.
the input is just
Yeah.
on marginal.
Marginal statistics and the LD